Okay, so we are very happy today to have Takehiko Mori from Chiba University. So Takehiko was born and grew up in Japan. After receiving a bachelor and master's degree from Chiba University, he enrolled in the doctoral program at the same university and continued. The area of expertise is operator algebra and their application. He has been studying connection between operator algebra and dynamical systems. Takehiko, please, you can start.
Okay, okay, let's get started. Hi, I'm Takehiko Mori, a doctoral student in Chiba University in Japan. Thank you for inviting me to BIMSA-Tsinghua Content Symmetry Seminar. It's a pleasure to meet you. I'd like to share ideas about application of operator theory for another area in mathematics. In this talk, I will speak about the Collatz conjecture and formalization of it by operator theory. First of all, I'll explain the Collatz conjecture and discrete dynamical systems. Let X be a set and F be a map on X. For non-negative integer n, nth iterate of F denotes as follows. And zeroth iterate of F is the identity map on X. And for positive integer n plus 1th iterate of F is the composition of F and nth iterate of F. The pair of X and F gives a discrete dynamical systems. For a point of X, the orbit of it is defined as follows. Let small of x in X. The orbit of small x is a set of images of small x by all nth iterate of F. If the map F is fixed, then we simply call it the orbit of X. On discrete dynamical systems, there is an important idea about the map and a subset of the total set, which is called the first return map or Poincare map. Fix a non-empty subset sigma of X and let X be a point of sigma. If there exists a positive integer n such that the image of X by nth iterate of F is in sigma, then we will let tau of X denote the minimum integer as such. And then let sigma dash be all X such that there is tau of X. And the first return map for F on sigma is the map P from sigma dash to sigma, defined by P of X is equal to the image of X by tau of X iterate of F. And this idea will be used afterwards to formalize the Collatz conjecture by the Cuntz algebras. From the point of view of discrete dynamical systems, are explained the Collatz conjecture. The Collatz map F is defined on the set of all natural numbers as follows. For an odd number n, f of n is equal to 3n plus 1. And for an even number n, f of n is equal to half of n. Then the Collatz conjecture states that for every natural number n, there is a non-negative integer n such that the image of n by n's iterate of f is equal to 1. That is, 1 always belongs to the orbit of every natural number n by the Collatz map. This conjecture is proposed by Rosa Collatz in 1937, and there are other names of it. For example, 3n plus 1 problem, Kakutani's problem, Yoneda's conjecture, and Ulam's conjecture. Many mathematicians have studied the conjecture for a long time, but it remains an open problem. According to our research by computers, the statement is true for every n less than 2 to the power of 68. Let's see examples. The orbit of 1 is composed of 1, 2, and 4. The orbit of 3 is composed of 1, 2, 3, 4, 5, 8, 10, 16. And the orbit of 7 is composed of 70 elements. And in the end of the first section, we introduce equivalence relations by maps. Let X be a set and F be a map. We define a binary relation on X as follows. Small x is related to y if and only if the intersection of the orbit of x by f and the orbit of y by f is not empty. It is easy to check that the relation defined as above is an equivalence relation. Consider the Collatz map. Then the following are equivalent. First statement, the Collatz conjecture holds. Second statement, for every natural number is equivalent to 1 by the Collatz map. And third statement, for every natural numbers are equivalent. And these equivalence relations are very useful in this study. Please keep them in the back of your mind. Second section, we formalize the Collatz conjecture by operator theory. We will recall some definitions and theorem of operator theory. Let H be a Hilbert space and T be a bounded linear operator on H. And let M be a closed subspace of H. When the image of M by T and the image of M by T star are included in M, M is called a reducing subspace for T. T star means the adjoint operator of T. Similarly, for a set A, which is composed of bounded linear operators on H, we say that M is a reducing subspace for A when M is a reducing subspace for every T in A. And B of H denotes the set of all bounded linear operators on H. When M is the set of only 0 or M is H, these are called trivial subspace. Um, let a norm map from B of H to the set of all real numbers. And we define by the following. Then it is a norm on B of H, and we call it the operator norm of B of H. Now let's define the sister algebras on H. Let A be a subset of B of H. A is a sister algebra when the following conditions hold. A is a subalgebra of B of H. If T belongs to A, then T star belongs to A. And A is closed for the topology induced by the operator norm of B of H. For finite operators S1, S2, and Sn, the sister algebra generated by them will be denoted by C star of S1, S2, and Sn. And next, we will recall the commutant of the set of bounded linear operators. For subset A of B of H, the commutant of A is denoted by A dash and defined by the set of all bounded linear operators on H, which are commutative for every element in A. And there is a well-known result about sister algebras and those commutants. The result will play an important role in this study. Theorem. If H is a Hilbert space on the set of all complex numbers and a subset A of B of H is a sister algebra, then the following statements are equivalent. First condition, A has no non-trivial reducing subspaces. Second condition, A dash is equal to the set of products of every scalar and the identity operator I on H. And third condition, if P in A dash is a projection, then P equals 0 or P equals I. And fourth condition, if X is any non-zero vector in H, then H is equal to the closure of AX. And these conditions are equivalent. For the proof of this theorem, see, for example, a course in operator theory by John B. Conway. And from now, we will discuss 3 ways to formulate the Collatz conjecture by operators. Fix F be the Collatz map. Let H be a Hilbert space on the set of all complex numbers with countably infinite dimension. That is, there exists a countably infinite completely orthonormal system. CONS means complete orthonormal system. Then define a bounded linear operator T by TEN is equal to EF of n, where n is a natural number. And this definition is valid because the cardinality of the inverse image of every natural number by f is at most 2. And furthermore, the following lemma hold. And for every natural number n, the closure of the set of all images of En by every operator in C star of T is included in the closed linear span of every En where M is equivalent to N. And from this lemma, we can obtain the next result. And theorem, if C star of T has no non-trivial reducing subspaces, then the Collatz conjecture holds. The theorem states that an operator theoretic condition is a sufficient condition for the Collatz conjecture. So we can deal with the Collatz conjecture by using functional analytic ideas, for example, limit operation, continuousness, and uncountable infinite. And the proof of the theorem is not so long by using the formal lemma. And for every n, for every natural number n, the closure of C star of T En is a reducing subspace for C star of T. If C star of T has no non-trivial reducing subspaces, then the closure of C star of T En is equal to H. Then, according to the formal lemma, the closed linear span of every En where M is equivalent to N is equal to H. It follows that every two natural numbers are equivalent. Thus, the Collatz conjecture holds. This is the first way to consider the Collatz conjecture by operator theory. Next, we increase the number of operators to formulation. The second way of formulation is to use two bounded linear operators. Define T1 and T2 as operators on H satisfying the following conditions. For T1, the image of En is E3n plus 1 when n is odd and 0 when n is even. For T2, the image of En is 0 when n is odd and E half of n when n is even. We are considering a decomposition of the former single operator T. It is easy to check that T1 plus T2 is equal to T. And T1 and T2 are partial isometries. So the norm of T1 and T2 are equal to 1. These properties lead the next results. For every natural number n, the following relational expression holds. The closure of system T or En is the closed linear span of every En where M is equivalent to N. And in addition, the next lemma holds. If P in the commutant of C star of T1, T2 is an orthogonal projection, then PE1 is equal to 0 or PE1 is equal to E1. And from these two lemmas, we obtain the next theorem. For two partial isometries T1 and T2, and the following are equivalent. First condition, sister algebra generated by T1 and T2 has no non-trivial reducing subspace. The second condition, the Collatz conjecture holds. So it turns out that the Collatz conjecture is equivalent to a property of a sister algebra. This is the first result about the equivalency between the Collatz conjecture and some propositions for sister algebras. Just a moment. And it turns out that the Collatz conjecture is equivalent to some proposition for sister algebra. And for this relation, we can replace a sister algebra with the Cuntz algebra in the next formulation. The Cuntz algebras are universal sister algebras generated by isometries. They are simple as sister algebras. And we say that a sister algebra is simple when there are no two-sided closed ideals. And the the definition of Cuntz algebra is as follows. For a natural number n more than 1, the Cuntz algebra of n is the universal sister algebra generated by n isometries. Isometries satisfy the following conditions. Joachim Cuntz studied these algebras and proved they are simple. And for any isometries satisfying the relation above, then the sister algebra generated by them is isomorphic to the Cuntz algebra. And we define two disjoint subsets of the set of all natural numbers by and one is the set of every odd number which is congruent with 1 or 5 modulo 6. And N2 is the image of N1 of F. Then we consider the first return map for F on the union of N1 and N2. And for some calculations, we can find some properties of the map P. It turns out that P is defined on both the union of N1 and N2. And following two propositions hold. And first proposition, um, both of the restrictions of P on N1 and N2 are injections, and the image of N1 by P is N2, and the image of N2 by P is the union of N1 and N2. This proposition reads the relational expressions of the Cuntz algebras. Next proposition states the equivalency about the Collatz conjecture. And second proposition, the Collatz conjecture holds if and only if 1 is in every orbit of n by p. And let's start the third formulation. And consider the Hilbert space H, whose complete orthonormal system is a sequence of ENs, where n runs over n1 union n2. And then we define bounded linear operators T1 and T2 as follows. And for T1, T1 En is equal to EP of n when n is in n1, and 0 when n in n2. And for T2, T2En is equal to 0 when n is in n1, and EP of n when n is in n2. And we define new two operators S1 and S2 as S1 equal T1 star T1 2 star and S2 equal T2 star. And in this setting, the next proposition holds. If T1, T2, S1, and S2 are defined as such, then the sister algebra generated by S1 and S2 equals the sister algebra generated by T1 and T2. And more, the sister algebra is isomorphic to the Cuntz algebra O2. And according to the property of P, S1 and S2 are isometries satisfying the conditions of the Cuntz algebras. Then we have the next results. Considers equivalence relation on N1 union N2 by the map or the map P. And for every n in N1 union N2, the following two sets are the same. And in addition, next lemma, if Q in the commutant of sister algebra generated by S1 and S2 is a projection and the Collatz conjecture holds, then QE1 equals 0 or E1. These lemmas are similar on the second formulation of the Collatz conjecture. And we obtained the following equivalency. Theorem. The following are equivalent. Sister algebra generated by S1 and S2 has no non-trivial reducing subspaces. And no, this condition is equal to the Collatz conjecture. For modalities, please see the preprint on archive and the paper on the journal Advances in Operator Theory article 37. And this paper was published on the last month, and the title is the same as preprint one. And thirdly, We will discuss the generalization for formulation of the Collatz conjecture by operator theory. We will consider more generalized cases. First, we introduce the bounded condition for maps. Assume that X is an arbitrary set whose cardinality is countably infinite, and F is a map on X. And we introduce a bounded condition for F. When there exists disjoint subset x1, x2, and xk of X, where k is in a natural numbers, such that first condition and the union of xi's equal x. And second condition, restriction of f on xi is injective for every I. And we say that f satisfies the bounded condition. This condition is a bounded linear operator on Hilbert space. Hereinafter, we will assume that F satisfies the bounded condition. And then there is a problem. For given X and F, does it hold that X is equivalent to Y and by map F for every XY? Um, it is not always true. For example, the identity map is map satisfying bounded condition, but identity map is not satisfying this problem's property. For example, qx plus 1 function. Let q is a positive integer, positive odd integer. The qx plus 1 function fq is defined by fq of n, a natural number of fq of n equal qn plus 1 when n is odd number, and fq of n is equal to half of n when n is even. This is like a class map. And the second example, 3x plus d function. Let d be an ordered integer, and the 3x plus d function fd is defined by as follows. Fd of n is equal to 3n plus d when n is odd, and half of n when n is even. Now, let's consider an operator theory. Let H be a Hilbert space on C with dimension of H is countably infinite. EX it be a complete orthonormal system for H. We define T on H by TEX equal EF of X, where X in X. According to the bounded condition for F, we can check that T is a bounded linear operator. And next lemma holds. For every small x in X, C star of TEX, the closure is included in cross linear span of EY, where Y is equivalent to X. And this lemma reads the next theorem. If C star of T has no non-trivial reducing subspaces, then X is equivalent to Y for every xy in X. And the proof is similar for a first formulation of the Collatz conjecture by a single operator. And this is a generalization. And next, we define k partial isometries T1, T2, and Tk in BOH by TIEX is equal to EF of X when X is in Xi and TIEX equals 0 when X is not in Xi. X1, X2, and Xk is the composition of X. So Ti here can be defined as above. This setting induces the following relations. For every X in S, the closure of C star algebra generated by T1, T2, and TKEX is equal to closed linear span of EY, where Y is equivalent to X. Then we can obtain the theorem. If C star of T1, T2, and Tk has no non-trivial reducing subspaces, then X is equivalent to Y for every xy in X. And this means C star algebra's property is a sufficient condition to X is equal to Y for every xy. The problem. And secondly, we introduce a condition for maps separating condition. Let n is a natural number and sigma be a cyclic permutation of the set of 1, 2, and defined by the following. 1, 2, 2, 2, 2, 3, and n minus 1, 2, and n 2, 1. For an n tuple of numbers, I1, I2, and In, we say that it is a periodic if I sigma j1, I sigma j2, and I sigma j of n is not equal to I1, I2, and In for every j less than n. And then we define a splitting condition from map. Let X in X when the following conditions hold. First condition, there exists n in satisfying the nth iterate of f of x is equal to x, and second condition for the minimal n other bar, and the n tuple I1, I2, and In, and in and this is such that nj minus 1's iterate of f of x is in xij, where j is more than or equal to 1 and less than or equal to n. This tuple I1, I2, and In is a periodic. And then we say that f satisfies the separating condition for x. Um, there is an example, and qx plus 1 function for q equal 5 Mersenne numbers. And let x1 and x2 be the sets of all positive odd numbers and even numbers. When q equal 5, f5 makes a loop as follows. 1 to 6 to 3 to 16 to 8 to 4 to 1. And since 7 tuple 1 2 1 2 2 2 2 is a periodic, so f5 satisfies the separating condition for 1. And let q be a Mersenne number, such that q is equal to some case power of 2 minus 1. And fq of 1 equal to k, case power of 2. And if q square of 1 is equal to k minus 1's power of 2, iterations go to 1. So, and k plus 1 tuple 1, 2, and 2, and 2, 2, 2, 2, 2, 2 is a periodic. Hence, fq satisfy the separating condition for 1. And next, 3x plus d function. Let d be an odd integer. Let x1 equal every odd number and x2 equal every even number. Then f d of d equal 4d. Again fd again fd. So then we obtain 2d and some iterate of fd of d equal d. And 3 tuple in 1, 2, 2 is a periodic. Hence, fd satisfy the separating condition for d. For separating condition, we have the following lemma. Let x in S and N be a closure of system of T1, T2, and Tk and assume F satisfy the separating condition for x, and then and C star of T1, T2, and Tk the closure is just n for every a, and it that is in n, not n0. And this lemma leads the next theorem. And theorem, let small x in X and assume F satisfies the separating condition for X. Then, if Y is equivalent to Z for every YZ in X, then C star of T1, T2, and Tk has no non-trivial reducing subspaces. That is, is condition is algebra has non-trivial reducing subspaces is necessary condition to the proposition every y and z is equivalent. This proof is short by lemma. By the assumption the closure of C star of T1, T2, Tk, and Ex is equal to closure linear span of Ey, where y is equivalent to x. This is equal h. And from the former lemma, we obtain that C star of T1, T2, and Tk's closure is equal to h for every a in not zero element. And this implies that C star of T1, T2, and Tk has no non-trivial reducing subspaces. This follows theorem in the Conway's book. And thirdly, we introduce the Kuntz-Krieger condition for map. And we introduce the notion of the Kuntz-Krieger condition F on next. This idea comes from a special class of sister algebras given by Cuntz and Krieger. In a class of sister algebras and topological Markov chains, Joachim Cuntz and Wolfgang Krieger. The Krieger algebras definition is as follows. For natural number k more than 1 and k times k matrix A with entries in 0 or 1 such that no row is 0. And the Kuntz-Krieger algebra is the universal sister algebra generated by partial isometries S1, S2, and Sn satisfy the following condition. This is like Kuntz algebra. In fact, the Kuntz algebra is the Kuntz-Krieger algebra. And next, we consider a Kuntz-Krieger condition for map. When the following hold, we see that F satisfies the Kuntz-Krieger condition. First condition, F is surjective. And second condition, for every J, there exists a large J, this is subset of the set of 1, 2, and K, such that f of xj is equal to the union of xi, where I is in J. Now we see that F satisfies the Kuntz-Krieger condition. Uh, this setting leads next proposition. If F satisfies the Kuntz-Krieger condition, then there exists the Kuntz-Krieger algebra OA and a surjective star homomorphism phi. From OA to C star algebra generated by T1, T2, and Tk. There are examples. Qx plus 1 function for q equal 5 are Mersenne numbers. For q equal 5, n1 is a set n is congruent to 1, 3, 7, or 9 modulo 10. And n2 is the image of n1 by f5. And consider the first return map for f5 on n1 union n2 denoted by p. Then p satisfy the Kuntz-Krieger condition. And for k, for k be a natural number more than 2, and the Mersenne number q equal k's power of 2 minus 1. And let n1 is the set of an odd number such that there exists natural number L to n is congruent to L's power of t modulo 2 times square of t square cube. And n2 is the image of n1. And consider the first return map for fq on n1 union n2 denoted by p. Then p satisfies the Kuntz-Krieger condition. And finally, 3x plus d function. Let d be an odd integer and k be the integer and non-negative integer satisfying that k's power of 3 divides d and k plus 1's power of 3 doesn't divide d. Then define the set n1 and n2 as follows. Then consider the first return map for ft on n1 union n2, and then p satisfies the Kuntz-Krieger condition. So first return maps plays an important role in this result. and uh, there is differences Conway, Guns, and Kuntz Krieger. Um, and um, okay, I finished the talk.
Okay, thank you. Question now? I have several questions. But if you have questions, I can start. So can you hear me? Yeah.
Yes, yes.
So can you come back to slide 16, please?
Okay.
16, 16,
Mm, What?
16, 16. So slide
16.
16. Yeah.
Okay.
So the theorem. Um, the theta algebra in your theorem is the Cuntz algebra O2 in this theorem. The theta algebra,
Sorry.
the theta algebra in
Hi.
your theorem. Yeah. Yeah. Can you hear me?
Okay, okay.
The theta algebra in your theorem is the Cuntz algebra O2.
Um, C-star algebra generated by S1 and S2.
Yeah.
It is isomorphic to Kuntz algebra also.
So So you reformulated the Collatz conjecture as a property of the Cuntz algebra O2.
Yes, yes.
It's fantastic, no? It's an open problem for the Cuntz algebra O2, this reducing subspace problem. So
Sorry, your voice.
uh,
Oh,
you cannot hear me properly, no?
um, I can't hear you properly.
So you said the
Um,
Collatz conjecture is equivalent to a property of the Cuntz algebra. It's
that is, yes. So, uh, I obtain the Kuntz algebras representation has no non-trivial reducing subspaces is equivalent to the Collatz conjecture.
so this property for Kuntz algebra is it a well-known open problem for Kuntz algebra? Or did you try to ask operator algebraists whether this is known for Kuntz algebra? Regardless of the Collatz conjecture, just Kuntz algebra. This property is this this is a well-known open problem for Kuntz algebra or what? Because
Mm, um, um, Let me see. Um, and algebras property. Uh, um, I'm sorry, I beg your pardon.
I said I was very surprised that you can reformulate this very famous conjecture in terms of the property of the
Uh,
Kuntz algebra, which is
uh,
like the Kuntz algebra is more or less independent of the Collatz conjecture. But it's very interesting. I want to say I'm surprised.
thank you. Thank you. Do you have any questions?
Yeah. Any question? Yeah. So I have another question. So are you interested in proving the Collatz conjecture using operator algebra then? Did you try to work on that? To to use operator algebra to prove the Collatz conjecture? Are you?
Reason? Motivation?
No, I said, are you, do you plan to work on the Collatz conjecture using operator algebra? Solve this conjecture.
Eh, um, First, I wanted to uh, make application of operator theory for number theory.
Mhm.
And I knew the Collatz conjecture, and this is a simple statement, but difficult. I think that is uh, difficult because number theory consider a finite discussion. So if discuss infinite property, uh, for example, limit, infinite dimension, continuously. These are tools of operator theory. So I think operator theory can treat the cross conjecture. Makes sense.
Yeah, yeah.
I have a question. So, is a sister algebra generated by S1 and S2? And does this sister algebra has, can you prove this sister algebra does not have non-trivial finite dimensional subspace?
Excuse me, I beg your pardon.
Oh, okay. My question is, can you prove the sister algebra generated by S1, S2 has does not have finite dimensional subspace?
Yes, infinite dimensional subspace. Uh,
Finite dimensional subspace. It is possible to prove it.
um, Sorry, what do you say? And Is there finite dimensional subspace for sister algebras?
Yes, my question is, is it possible to prove this sister algebra does not have finite dimensional subspace? I think it is easier, maybe. I don't know.
Finite dimensional.
Are you saying that the finite dimensional invariant subspace?
Yes. To prove does not exist.
It
Yeah, Cuntz
is.
algebra is simple and infinite dimensional, so it cannot act on finite dimensional space.
When considering Cuntz algebra, so it's it not exists finite dimensional subspace, but in general it is not trivial.
Oh, it's interesting, I think. Thank you.
Any other question or comment from the audience or online? Okay, so if there is no more question, let's thank you again. This is very, very interesting. Thank you very much.
Thank you. Thank you.
Ah.